teammate is 虚风菜. So the project for the course CS765 is called Interactive, Interpretable, and User-Friendly Dimensionality Reduction Visualization. So we just include the link for our demo in the final report. So let's first go into the link for MNIST. We can see that we can directly access this link from CS servers. And let's directly jump into how it works. So when we hover on one dimension reduction algorithm, for example TC, we can see that we can see the exact image in such dimensionality reduction figure. For example, here it shows finger or we call the logit 1 in this visualization, which is really nice. And the more interesting thing is that our algorithm or our visualization can actually show the high dimension neighbors and the low dimension neighbors, right? We can see that in this case, the neighbors under such two cases looks really similar, which are all digits 1. But they also but they also have some difference in terms of shape, right? But when we change it into other numbers, for example, we can find this number 5, right? The Hoover point is 5, but the high dimension neighbors and low dimension neighbors are quite different, right? So so how can we know which those high dimension neighbors and low dimension neighbors locate, right? We can, the neighbors are annotated with different colors. For example, the low dimension neighbors are annotated with color blue, and high dimension neighbors are annotated with color green. Yeah, so the whole point is annotated with pink, and the coincident neighbors are annotated with red, as you can see in this figure. Yeah, so that's great, and we also show the similarity scores, right? The exact value for such scores, which can better assist the user experience. Yeah, the same story happens for UMAP, which is another popular dimensionality reduction algorithm, right? We hover on one data point, and we can show the actual index, high dimension neighbors, low dimension neighbors in index, right? And we can see that the overall field, right, the overall layout is created using the physical force field, which could simulate how the 2D layout could be formed using the physical field, right? So when we use this field, we can get rid of a bunch of restrictions about the distance or the similarity matrix. We can just use the similarity score, or we call distance score, for point wise. For example, if we know that the distance score between this uh, digit and that digit, we can get such layout, right, which is quite convenient and general. Yeah, so UMAP follows the same story as TC, but we make this finger, right, pair by pair, side by side. It means that we can directly compare and have a look at how such two-dimensionality reduction algorithm works and how they differ from each other. Yeah, yeah, and in this case, we may find that um, also in UMAP, the high dimensionality neighbors and low dimensionality neighbors perform similarly at most time, but at some point they perform very differently. For example, in this case, right? Yeah, so this is the overall layout, and we offer more flexibility for users to interact in our website. For example, if a user they adjust many parameters and they don't know what is the default setting, so let's just click on reset, and we can see that this visualization just got back into the default setting. Yeah, and we can also let you choose the the data set, for example, cipher 10 and MNIST, and we can even let users upload files. For example, when we click on upload, user can choose files, and they may in the future choose whatever files they like. Yeah. And when we have new parameter settings, we can let user execute the settings and load new dimensionality reduction analysis. Yeah, and for the 2D layout, user may also choose right whether it's high dimensionality similarity layout which correspond to the first row, right, or the low dimensional similarity layout which corresponds to the second row. Yeah, this is the result for MNIST. And we have another demo for Cypher10. Let's go into this link, and we can see that Cypher10 actually has a different distribution than MNIST. And Cypher10, right, the distribution of Cypher10 dimension reduction 2D figure is more tight compared to the MNIST, where MNIST distribution is more uniform. And we can see that because the Cypher10 dataset is much more complex than MNIST, so the neighbors in low dimensionality and high dimensionality are not quite accurate. For example, if we find one airplane right at the hover point, and we can see that there are even some animals classified as nearest the top three neighbors. This is not quite straightforward for us to think about, right? And here is the results on UMap, and we can find the same story. Yeah, the overall setting is similar to the MNIST setting, and the only difference is in the data set. And again, you can try differences, run analysis, right? And you can find the differences between such TC and UMap visualizations. Yeah, this is our project, and thanks for your time to watch my demo. Yeah, thank you.